Welcome back to the Deep Dive. Today we are leaving the abstract theory behind for a bit. We're getting straight into the foundational rulebook of electrical safety. That's the National Electrical Code.
Mm-hmm.
For anyone running power, electricians, engineers, even just property owners, this book, the 2023 edition, NFPA 70, it's basically non-negotiable.
Absolutely. It really is the core set of rules for making sure electrical installations are safe. You can't really do the work properly without it.
Now, the NEC, it's a massive document, as you know. But we're going to zero in today on just one part.
Yeah.
Chapter 2.
Right.
That's the chapter dedicated to wiring and protection.
Yeah, think of it as the guide for making sure your wires, your conductors are sized right and protected properly from overcurrent.
Okay.
The whole code, it's got 9 chapters, covers everything from general stuff, wiring methods, all the way to like special buildings and communication systems.
Right.
But chapter 2 is fundamental. It dictates how much current those wires can safely handle. Our sources today really take us into the details, the often overlooked specifics, especially around sizing those main power lines.
The feeders and service conductors.
Exactly. Those are the terms that the code uses.
Okay, just so we're all on the same page, what's the quick and dirty difference for the listener between feeders and service conductors?
Sure. It's mostly about location, really. Service conductors, they're the ones bringing power into the property right up to the main disconnect, the service equipment.
Like the main breaker panel.
Usually, yeah. Or a main switch. Then the feeders, those are the large wires leaving that main panel to power other big loads or maybe sub-panels somewhere else, like out in a barn or a workshop.
Got it. So sizing calculations apply to both.
Oh, yeah. You're calculating the load to size all of them properly. It's all about preventing overheating, preventing fires. That's the goal.
Okay, so our mission today then is to show you the astonishing complexity you can find hidden in one very specific area. Electrical load calculations for farm systems.
Mm-hmm.
We're drilling right into section 220.102. This is where precision and really knowing how the customer uses power, well, it determines the entire system design.
It really does.
Okay, let's unpack this.
So the basic challenge in any electrical design, farms included, is figuring out that load calculation. We need to know the maximum current the system might draw.
Right.
But here's the reality check. No farm, no house, no factory, nothing runs everything at its absolute maximum possible load all at the same time. It just doesn't happen.
Okay.
And if you actually design for that theoretical 100% possibility, your installation would cost a fortune, mostly in copper wire, and it'd just be way, way oversized. Massive overkill.
So you'd be wasting money.
A lot of money. And that's why the code includes demand factors. These aren't just guesses, they're standardized, approved reductions you can take on the calculated load. They're based on decades of professional experience, industry testing, engineering knowledge about how things are actually used.
Real-world usage patterns.
Exactly. Usage patterns. They let us design more efficiently, save on cost, while still maintaining, and this is critical, rigorous safety margins.
Right.
And Section 220.102 gives us the specific, detailed rules for figuring out these farm loads.
And right away, the rules split the property. It's like two different electrical worlds on one farm. We start with 220.102A, which covers the farm dwelling unit.
Yeah.
The house, basically.
The farmhouse itself, yeah.
And the default seems pretty simple at first glance. Calculate the house load using the standard rules for dwellings, usually Part 3 or Part 4 of Article 220.
Which makes sense. A house is a house.
But, this being the NEC, simple rarely stays simple for long.
Right, because the code has to acknowledge that a farm isn't just a house with a big yard or a barn. It's often a single interconnected electrical system. And those residential needs and the heavy agricultural demands, they can overlap, sometimes in ways that create specific risks, especially thermal risks, like overheating.
Okay, so this is where it gets really interesting then. Our sources point out this incredibly specific exception, a situation where you're actually prohibited from using the standard, often more streamlined, Part 4 calculation for the house.
That's the key detail.
And it only happens, apparently, when 3 specific conditions line up, all at the same time. 1, the dwelling unit itself has electric heating.
Big load number 1.
2, the farm uses certain high-demand equipment, specifically electric grain drying systems.
Big load number 2, often seasonal, but huge when it's on.
And condition 3, this seems crucial. Both the house load and these heavy farm loads, like the grain dryer, are supplied by a common service, one main feed from the utility.
That specific combination, electric heat in the house, electric grain drying on the farm, all fed from a single service. That's like an electrical perfect storm scenario, potentially.
Why is that combination so critical?
Well, think about it. Grain drying systems, when they run, they pull enormous amounts of power, and often for sustained periods, hours, maybe days.
Right.
Electric heating in a house, same thing. It's a massive load, and it runs for long stretches, especially when it's cold.
Okay, I hear you going.
So imagine a cold fall day, harvest is in, the grain dryer is running full tilt, and the electric heat in the house kicks on because the temperature dropped.
Suddenly, the total demand on that single service could spike dramatically.
Exactly. Radically shifts the demand profile. The code recognizes that in this specific scenario, the risk of overloading those main service conductors is just too high to rely on the normal diversity assumptions built into the standard residential calculations.
So the typical assumptions about, not everything being on at once in a house, that they break down here.
They break down. The usage profile is just too intense, too concentrated. Safety has to override the potential for calculation efficiency in this case. You can't use part 4, you have to use the more detailed part 3 method.
That's fascinating. It's risk management literally written into the electrical code.
Precisely.
Okay, so let's shift focus. The house is handled. Maybe with that special exception, maybe not. But what about when we leave the farmhouse porch and head out towards the barns, the pumps, the equipment sheds? Does the math change completely for section 220.102b, the other than dwelling unit loads?
Oh, it changes dramatically. Yeah. For any feeder or service that supplies a farm building, or even just an outdoor load that has 2 or more separate branch circuits.
Which is probably most farm buildings, right? A light circuit and outlet circuit.
Almost certainly. Any functional farm structure is likely to have at least 2 circuits. So for those, you must use the demand factors detailed in table 220.102b. There's no other option.
And this is where it gets really interesting. Because as I understand it, you're not just doing one calculation to find the maximum load.
No, not at all.
You have to perform, 3 entirely different calculations based on different criteria?
That's right. 3 distinct calculations.
And then you have to design your service, size your wires, based on the greater of those 3 results.
Exactly. The largest number dictates the minimum size.
It's like you're planning for the worst-case scenario, no matter how that worst case happens to occur.
That's a perfect way to put it. You're essentially guaranteeing that your conductors are sized to handle the absolute heaviest load the non-dwelling parts of the farm will ever place on them, regardless of how that load is made up at any given moment. Simultaneous use, a big motor starting, or just a lot of miscellaneous stuff running.
Okay, so let's break down those 3 calculations you have to compare. What's the first one? The first one seems the most intuitive, maybe. You calculate for all the loads that you expect to operate simultaneously at the same time.
Correct.
So if you know the barn lights, the ventilation fans, maybe an automated feeding system, if they all run together routinely.
Then you add up their loads and apply a full 100% demand factor. No reductions allowed there. If they're going to run together, you need the capacity to supply the full current they need. Simple as that.
Okay, 100% for simultaneous loads. What's calculation number 2?
Calculation number 2 focuses specifically on motors. And farms, as you can imagine, rely heavily on machinery with large motors. Pumps, compressors, conveyors, grinders.
Lots of motors.
Lots of motors. So for the largest single motor served by that feeder or service, you have to calculate its load at 125% of its full load current rating.
Wait, 125%. Why the extra 25% on top of its normal running current? That seems like a significant padding.
It might seem like padding, but it's absolutely not. It's a critical safety factor that addresses a physical phenomenon called inrush current.
Inrush current.
Yeah. Think about starting something really heavy, like getting a freight train moving from a dead stop.
Takes a huge surge of effort initially.
Exactly. A huge surge of power just to overcome inertia before it settles into its cruising speed. Electric motors do the exact same thing electrically. When they first switch on for a very brief moment, they draw significantly more current than they do once they're running steadily.
Okay.
That 125% factor ensures the conductors, and often the overcurrent protection too, can safely handle that sudden temporary burst of energy without tripping breakers nuisancely or worse, overheating the wires. It protects the system from that momentary spike.
Got it. So not padding, but protection against that startup surge.
Precisely.
Okay, so we've got simultaneous loads at 100%, largest motor load handled at 125% for inrush. That seems to cover the known consistent demands. But what about everything else? All the, ancillary equipment, the stuff that turns on sporadically, Small tools plugged in here and there, maybe an occasional water heater in a workshop. The loads that you don't expect to run simultaneously with the main group and that are not the single largest motor.
Right. And that brings us to calculation number 3. And this, I think, is maybe the most sophisticated part of the NEC's approach here, balancing safety with farm efficiency.
Okay.
This calculation applies to what the code simply calls all other loads, everything that wasn't covered in calculation 1 or 2.
The leftovers, basically.
Sort of the leftovers, yeah. And this is where those tiered demand factors really kick in. It reflects the statistical reality, the probability that as you add more and more miscellaneous, unrelated equipment,
The chances of all of it running at the exact same time gets lower and lower.
exponentially lower. Exactly. It's highly improbable they'll all be on simultaneously.
Okay, and this is where the code allows for some significant efficiency, dropping those load requirements quite a bit.
Yes, this is where the balance comes in.
How are those tiers structured?
Yeah,
It's based on the load in amperes, calculated at 240 volts, right?
right. It's based on the total amperage of these other loads at 240 volts, and it's a steeply graduating scale.
Okay.
For the first 60 amperes of this all other loads category, you still calculate it at 100% demand factor.
So full load for the first chunk.
Right. That covers the sort of baseline use, the smaller loads that are more likely to be on, basic stuff. But once you get past that first 60 amps, the requirement drops significantly. For the next 60 amperes of these other loads, so from 61 amps up to 120 amps total, you only need to apply a 50% demand factor.
Yeah, okay, cut in half.
Cut in half.
Yeah.
And then finally, if you have any remaining load in this category beyond that first 120 amperes combined, anything above 120 amps,
Yeah.
you only apply a 25% demand factor to that remainder.
Hold on, 25%. The code lets you potentially size your main wires to carry only 1/4 of the nameplate capacity of all that remaining equipment.
That's what it says.
That sounds like, it sounds like a huge gamble just to save some money on copper wire.
Yeah.
What stops someone from just, conveniently classifying some really critical equipment into that 25% bucket?
That's an excellent question, and it gets to the heart of why the code is structured this way. But it isn't really a gamble. It's applied statistics, physics informed by decades of real-world data.
Okay, how so?
Well, first, remember calculations 1 and 2. The code is very strict about identifying what must be considered simultaneous, that's 100%, and what constitutes the largest motor, that gets 125%. Those are handled first. Everything else falls into calculation 3 by definition.
Right.
Second, the reason for those big reductions, down to 50% and especially 25%, is that statistical certainty we talked about. It's backed by enormous amounts of data on actual electrical usage in agricultural settings over many, many years.
So it's based on observed reality.
Absolutely. Imagine a really large farm operation. Maybe they have, say, 50 different small 1 kilowatt heaters scattered across various outbuildings for preventing pipes from freezing or something.
Right.
The total connected load is 50 kilowatts, which is substantial. But is it remotely plausible that the farmer or any single farm process would require or even accidentally turn all 50 of those heaters on at the exact same moment?
No, probably not. Highly unlikely.
Extremely unlikely. So that 25% factor applied to loads above 120 amps. It's the engineered, statistically validated compromise. It ensures the conductors are still adequately sized for the likely maximum draw from that diverse group of loads without forcing the owner to pay potentially tens of thousands of dollars extra for copper capacity that will realistically never, ever be used.
So it prevents massive, unnecessary oversizing for improbable scenarios.
Exactly. Safety is paramount for the definite loads and the highest risk loads, like motor starting. Efficiency and cost effectiveness are factored in for the diverse, statistically less likely simultaneous loads.
Okay, that makes more sense. That graduated reduction, 100% down to 50%, down to 25%, it's really the core of the engineering intelligence here.
It really is.
Balancing the risks, the inrush current, the known simultaneous stuff with the reality of diverse, non-coincident use for everything else.
Precisely. And then, crucially, you perform all 3 calculations. The 100% simultaneous, the 125% largest motor, plus other motors at 100%, and this tiered calculation for the rest.
And you take the single biggest number, the largest calculated ampacity, from those 3 results.
And that number becomes your minimum required capacity for the feeder or service conductors. You must size them to handle at least that much current.
So what does this all mean? When we step back and look at this deep dive into just one section, 220.102,
Yeah.
it shows that the National Electrical Code is It's far more than just a simple list of rules or a checklist. It's really a complex mathematical engine
That's a good way to put it.
designed to optimize both safety and efficiency,
Yeah.
but critically, based on the specific application, how the power is actually going to be used.
Absolutely. We saw how the code gets incredibly specific about risk, identifying that unique combination, electric heat, electric grain drying, common service, and saying, nope, standard assumptions don't apply here anymore.
Right, changing the calculation method entirely for the dwelling in that case.
Mm-hmm. And then we saw that balancing act for the non-dwelling loads, making sure you absolutely cover the high-risk motor startups with that 125% factor.
While still responsibly using those tiered 50% and 25% demand factors for the bulk of the other equipment, recognizing diversity.
Exactly. It's a sophisticated approach.
So the underlying principle, it seems, is that deep knowledge of the application, understanding how and when the electricity will be used on that specific farm, that knowledge critically determines the correct calculation method. The NEC demands that level of understanding.
It really does. And, that brings up an interesting thought, maybe something for you, the listener, to consider.
Okay.
If the code is this specific, this rigorous, about analyzing usage patterns in a farm environment to achieve safe and efficient design, how many other types of installations, maybe ones we think of as simpler, might benefit from a similar approach?
Like what?
Well, maybe large apartment buildings, university campuses with diverse labs and dorms, multi-tenant commercial spaces, places without a dedicated farm load section in the code. Could applying this kind of rigorous tiered demand factor approach based on a deeper analysis of actual usage patterns, could that unlock potential for even safer and maybe vastly more efficient electrical designs in those areas too?
Is there unrealized potential just waiting? Because we don't always analyze usage quite this deeply outside of these special cases like farms.
It's definitely a question worth asking. How much are we potentially over-designing or maybe even underappreciating risk in other contexts by relying on broader assumptions?
Interesting. Definitely something to mull over next time you're looking at an electrical plan or a spec sheet.
Food for thought. All right, that is all the time we have for this deep dive into the guts of the NEC and farm load calculations. Thank you for joining us.